So, okay, everyone, this will be our workshop 2024 for TTSM. Yes, it's on symbolic music generation, and the format we'll use is MIDI format. I hope people are kind of at least know what is MIDI. Who like work with MIDI here ever? Anybody? Okay, so my name is Jingwei Liu. I will be like your instructor, like who's been providing this workshop, and I'm a PhD candidate in computer music at UC San Diego. So yeah, it's my fourth year, and my work, actually my interest in symbolic music generation already like kind of lasted for 5-6 years before I joined UCSD. I mean, I started this kind of music research on music, on symbolic music. I mean, now people are more dealing with audios directly. So in your workshop, like next weekend with Tornike, he will talk about audio kind of, synthesis, music generation. But I think symbolic music was where people started. And when you think about music at first, right? Yeah, I mean, maybe the most you'll think about is like kind of like notational music, Western music, things like that. I mean, not necessarily Western music, but also like folk tunes, and anything like you want to, invent some notation to, write the music down on the paper, want to share it with people. Yeah, symbolic music is like what you use, right? You don't use raw audio directly. Like, how do you describe your music ideas? So I think there's still some place for, symbolic music generation, and it's more concise. It's mid-level representation. It doesn't have, a lot of data or, sampling a lot of numbers, like comparing to the raw audio. It's more concise. It's more like, it has more like musical meaning, I would say. Yes, the recording will be available for participants. Yes. Okay. But I think, yeah, this is a kind of interactive workshop. So it will be great if you can participate, really, like in the conversation, in I mean, asking questions, and make sure like you understand. Because if I'm going too fast or I'm not very clear about something, you can just, ask follow-up questions. So it's just for you to understand this concept. And I also shared a writing of myself on this topic. Okay, maybe let me see if I can find a paper. Okay. So yes, here it's called Impressive MIDI Format. I wrote it last year actually. Yeah, okay. I wrote this last year, so my slides will be kind of abstract because this is for, presenting, and mostly will be pictures and music, and I will just explain by mouth. That you want to read something more carefully. This is the kind of writing I did last year when I work on this project, and I think this will be kind of my last project on symbolic music generation, because there are limitations on symbolic music, right? Like, I mean, if you use kind of sound effect filters and more modern music production techniques, the symbolic kind of notations cannot reflect that precisely. So if we deal with, I mean, people most use symbolic music for classical music, but nowadays, as the age changes, more and more it's like R&B, hip hop, things like that. So less people are using notational music. But I think this work is still like has its own value. That's why I'm introducing this, and hope to give you a brief kind of a recap of what's going on in this field of symbolic music generation. Okay. So let me continue with this presentation. So first of all, This is the corpus like we used last year. Okay. So this is from the Bach solo cello. This is the example I used in my last workshop. So I can actually play this here. You can hear my computer sound, right? Okay, great. Okay, so I can play it here, but because I'm using MIDI format, I would recommend you, if you don't have this MuseScore. Okay, so in MuseScore you can open the music XML file and MIDI file directly in the interface. Okay, so this is free, a free kind of open source software called MuseScore. What's the name of this? Maybe not. I don't know people really. Yeah, it's called MuseScore. So you just search it on Google and just download this for free. And yes, notational music player actually. Yeah, for any kind of notational music, just play it here. So I will use it for yeah, our staff music. So let me play here. So there will be a score folder. Okay, so well-formed classical music, right? You can see just single line monophonic music and well written, well composed. So okay, so this was the example I used last year to demonstrate, and we did some generation using recurrent neural network. So to talk, so if you look into this score, right? Let me ask if anyone want to share like what you noticed, like what you think is like important for music generation. What kind of properties or features you will get from this thing to generate music? Anyone want to say something or share? No.
Друзья, активнее участвуйте, пожалуйста. Это по международному, так сказать. I just said the majority of people here are Russian, so I said that let's participate. It's not like a Russian workshop, you know. Please be active. Yeah.
I'm Chinese. I'm originally Chinese.
I think it's
actually,
duration
so.
and the tone, maybe.
Oh, somebody said something. Can you repeat, please?
Yes, can you
I think
see?
the duration and pitch tone of the note.
Yes, great. Yeah, that's answer. I also see something in the chat on the page. So yeah, it will basically be pitch and duration. If you think about this kind of staff music, the things you will extract from this kind of we are doing data processing, right? You need to get some data, you need to get some representation that you can use to train the neural network. So the first, like if you are given this kind of corpus, what you will just extract right from this score to generate your music, it will be pitch and duration. Okay, so for most people, this is the most obvious, like kind of prominent thing you notice. So let's talk about pitch and duration. Okay, here. Okay, velocity. Great. So for velocity, actually, it depends. So sometimes, I will show you later on in this score, in this MIDI file, there actually is no velocity change. So the velocity is the same. Okay, because for the score music, you are mostly given just a paper, a paper of just like this, what you can see. So unless sometimes they have this FF, MF, right? Or piano, or just this kind of dynamic marks, there might be some So it really depends on people. Like when you encode this file into this computer readable format, whether you include velocity or not. So some score has velocity, some score doesn't have velocity. It really depends on time. That's why you need to look into the MIDI file. This is what we will do today to, open this file as, some kind of human readable format, and then you can look into the different data and see what's encoded there, what's not there, and how you will extract this information. Okay. So for this course, actually, if you just read this, there's no really velocity change. I mean, at least for this visible, format. Let me see. Yes, durations are the same too in this one. Yes, but the duration is clearly, marked. Everything is 16th note, and this is readable, and it's encoded in this file. Okay. Yeah, accent, no accent. Yes, great. So, yeah, if you like to, can you explain what you mean accent or no accent here? Yeah, because I mean, at least in this kind of
Up
in this
and
score,
down, I think.
sorry, what?
I think he means matter. So up and down.
Oh yeah, so you mean the downbeat?
Up and down beats.
Yes. Great. Yeah. Yes, thanks. So yeah, this is also a kind of information I will talk about later on. Yeah. Thanks for bringing this up, because I didn't think that people will really notice this. So yes, so you will have this something called metrical structure, right? Like kind of metrical grouping. You have upbeat, downbeat, you have the measures. So this is resulted from your time signature, right? So you have a fixed time signature, and in the score, you can distinguish the beat position, or the beat structure. So this is also one information you can use in your system, right? BPM, yes. Yes, BPM here. Yeah, great. So BPM is also very important information, and it's also like interesting how you will deal with this. Everything will be covered. Thanks for bringing this up. So I think this will be a really useful workshop, because I think people are just mentioning things that's the same as what I'm thinking about. Okay, great. Thanks for this. And let's maybe continue with this, and I'll address your kind of concerns and questions one by one. So first is pitch, okay? The most kind of prominent thing is pitch. So pitch, how we encode pitch in using computers for this kind of symbolic music, okay? So we will have discrete note, because you can see it on this kind of, notational music. Okay, discrete pitch, especially when we deal with piano, I mean, if you deal with kind of string music, string kind of instruments, the pitch might be, sliding or something. That will that can also be encoded in MIDI, but it will be used some other. It's something called control message. Then you need to use another thing to denote, what's the center frequency or the center pitch, and how you slide the pitch. But here, the situation we are dealing with is this is not that complicated, okay? So we only deal with discrete pitch here. We don't really consider any, effect or pitch sliding, pitch change during the process. So to encode this pitch, I believe everyone here is kind of actually at least know the letter notation. Okay, like C4, what is C4, what is D4, what is C5, F3, things like that. Okay, the letter notation. So in computer, when you use MIDI to encode this information, okay, it is actually so your baseline. Okay, the baseline is C4. So C4 is 60. And then you just encode every, semitone adding 1. So in a chromatic scale, you have 12 tones, right? 12 semitones, and then you have 60 until 71 here. Okay, from 60 until 71. So this is one scale, 12 notes, and from C4 to C5, so you just add 12. Okay, so every semitone means +1 or -1. So if the tune kind of from C4 to C3, then you just -12. I hope this is clear. Yeah, just simple how you map this chromatic scale into the MIDI notes, because the most we will deal with is the numbers. Okay, and then if you have this kind of notation, you can do the manipulation, add, subtract, and all kinds of things, and move from one key to another key, from one note to another note. Okay, so the idea of using computer to encode music is how you use numbers, right? The most thing you'll use is numbers. You can use text to do the annotation, but your system, basically your neural network cannot read text, okay? Or neural network only deal with numbers. So important thing is how do you represent the music properties into the numbers, and the system can recognize the numbers and deal with the numbers. So this is the note, the MIDI note. And let's talk about duration. So some people said in our first, in this corpus, that everything is 16th note, but it's not typical. So for example, in this one, you can see there's various more different, duration values. So like quarter note, half note, whole note, eighth, 16th, dotted eighth, etc. Okay. So let me also play this one in MuseScore. Okay. Okay, so you can see there are more duration values, right? Let's see. Okay, so this is quarter note, the beat, and 16th, dotted eighth, even 32nd is here, right? Different note value, duration values. So except for that, what else did you notice here? Anyone like different from the previous previous song?
Harmonics. It's polyphonic.
Yes. So even our previous example, we only have one line, so it kind of monophonic. But here, the kind of harmony, right, kind of appears, but it's very rare. It's not like really polyphonic. I will see homophony, and the harmonics appear somewhere, okay, only to harmonize this. So so this will be a topic we'll deal with today. It's like, because if you know RNN, but we'll talk about RNN. RNN is a recurrent neural network. Okay, so it's sequential. So how do you deal with the polyphonic texture using neural networks? So this will be it's actually a huge problem. It's kind of troubles the researchers for many years already. And I don't think it's really solved yet. But we will find a way to kind of, approach this problem in our workshop. Okay, rhythmic pattern, yes. The rhythmic pattern is basically resulting from different duration values, right? You have different durations, then you have different kind of rhythm. And also, rhythm pattern. Can you explain more, like what do you mean rhythm pattern? Like, is there any fixed pattern or?
So there's different rhythmics. If in previous song it was just similar notes, ta 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 ta. Here it's like ta 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 ta. So like different length of notes and their combinations.
Yes,
so I think it holds information.
Yes, exactly. Yes.
Some of them, some of rhythmic figures repeat.
Yes. Also,
we'll
yes.
see.
Right. Yeah. Thanks for your answers. Yes. So actually, different kind of rhythm is resulted from these different duration values, and also this repetitive structure, right? As often seen in music. And actually, this kind of repetitive structure is our basis for music generation. Like because music generation means you use the previous thing to predict the next note, right? You're generating this music. But how can you do that? I mean, if there's no rule or there's no kind of how things operate in music, then it is impossible, right? If everything is random, then you cannot really predict the next note. I mean, there's a lot of repetitive structures, a lot of kind of internal dynamics in the corpus that you can capture, and then you can see, oh, okay, I know what's happening before, and now I kind of repetitive or alter this somehow, and then I can well predict the next event. Yes, different skills. Yes, different key signatures. So yeah, we dealt with the key signature before. I mean, it is useful for data augmentation. It's like you can transpose keys, right? If you transpose this key to another one, then you basically get another kind of set of nodes. Then you can augment your data set, and that can help you to train your neural network better. Okay. So yes, thanks for your participation. And yeah, we talk about pitch and duration, kind of most important thing. And now we'll talk about in MIDI. There are actually different units to measure time. Okay, so time is not something you think that's that easy. So for example, in this thing, you can read there's different notes. You can name them as quarter note, half note, whole note. But there's also BPM, right? So you are dealing with different kind of times. So we have actually 3 types of time in MIDI. The first is it's called clock time. It's like computer time, like MIDI clock. The clock pauses. It's like how computer divides the time. Okay, this is the smallest unit in computer. And you have quarter note, the bit length. So this is sheet music time. I call it sheet music time because when you look into the sheet, this is how you denote the time, okay, the duration. And there's also real time. Use seconds, milliseconds, or microseconds. Because when you play music, when you play a note in real life, when you hear is the length is not really in quarter notes or something like that. It's more like using seconds because you have to consider BPM also, right? The BPM also determines how long your note will last. So for those things, I think it's a good time for us to move into the notebook. Okay, the Jupyter Notebook. Anyone here ever worked with Jupyter Notebook before or Python? Okay, great. I saw some hands here. Thanks. Great. So, okay, let me switch to this thing. Okay. So first of all, let me introduce you. And this notebook will be shared, okay, in the group in our chat later on after the workshop. So let me look into this code. Okay. No, it's not the same thing. Okay, I will get into more details in this notebook. Give you more examples here. Okay, thanks. So first, this is the package we will use. Okay, so I also give some package introduction. The first Music 21 is a kind of Python-based toolkit for computer-aided musicology. So for dealing with in our context, when we deal with the symbols, we use this. So actually, this was active last year, but this somehow was taken down this year. But the function still works. Okay, we can still use the functions, but I think I don't know why they took this down, the documentation down somehow, but we'll still use that. This was some kind of very useful tool for many Python users, especially if you deal with classical music, the sheet music. This is something you use for computer-aided musicology. Okay, for at least 10 years, the past 10 years. So, If you don't have the package, you just use this. Okay, this command called pip install music21. I mean, you can pip install anything here. You just change this thing with your package number or package name. Okay, package name. Like you can pip install py MIDI-CSV. So this is also something you need to install by yourself. Okay. So if you already downloaded Jupyter Notebook, and highly possibly you already have pandas and NumPy downloaded. Okay, it is the kind of built-in package in your Python. So you don't need to download them separately, hopefully. But for the first two, you need to download them, by this pip install command. Or if you use conda, then you will see conda like install something. Okay, so okay. So for py MIDI-CSV is actually a Python library that bidirectionally converts between the binary MIDI format and the human readable interpretation of the contained data in text format expressed as CSV. So anyone know CSV here before? Okay, great. I saw some hand. Great. Yes. So CSV is kind of I mean, I don't know. So it's a textual kind of thing. I mean, the most important thing is it's in this human readable format. Okay, it's not like we have to use CSV, but we want to convert MIDI to some human readable format. Like we can read it, we can process this information, we can read it, we can understand the messages. Okay, and then we can have another tool to deal with this. So this is the kind of the goal for the reason for why we use this. Okay, and there is a built-in kind of package for us to do this, which is bidirectionally transform MIDI to CSV and CSV to MIDI. Okay, so we will use convert MIDI to CSV because MIDI is actually encoded in this binary number. Okay, so if you open MIDI file, just MIDI file, it's impossible to read it. You need to compile it. That's why we kind of need this package here to convert this to something we can read. And pandas is a Python data analysis library. We'll use the data frame here to do the data processing, which is standard. Pandas is a standard, built-in library in Python that people, use to deal with the data frames, data formats. And you write things like in the table, kind of like in this Excel format, right? And NumPy is the foundational package for scientific computing with Python. So when we deal with numbers, when we do different, number manipulation, NumPy is the package we will use. So these are the four main packages we will use here. Okay. Okay, so first, we want to convert MIDI to CSV. So this is pretty easy because it's dealt with by this package already. Okay, so let's see. So I have this CS1.1 pre. So this is actually my first example here. Okay, and I just see, okay, file. I use this file. It's a MIDI file. So songs. So actually, I have this Jupyter Notebook. And this called TTSM2, and I have a folder called songs, and I input my MIDI files here. That's how I call this file here, right? And then I see, okay, this is my file, and I want to use this thing called PM. PM is the py MIDI-CSV, right? This package pm.midi to CSV. And then I convert this MIDI file. Okay, this MIDI file to CSV string. So if you look into this CSV string, so now you can have a better understanding of what's going on here, right? So you have different types of events, like header, start, track, some numbers, okay, like tempo, time signature, and most prominent, like the majority is note event, right? Because you're playing different notes, and note on, note off, things like that. And here you can see how they encode this, right? Actually, yeah, this is the, okay, so this is the pitch. This is the pitch. So this is the MIDI number we just saw, right? The MIDI number here. So how you map these numbers into the letter notation. So this line is the note value or the pitch, and this is actually the velocity. So someone mentioned velocity here. So you can see all the velocity here is 100. Okay, so 100 and 0. 0 means no velocity, which means the note ends. Okay, so you can see there's actually no dynamic change in this MIDI file. Okay, everything is 100. So all you have is different pitches and duration. So this is the time. Okay, so you can see the time increases in the file, and this is how we can compute the duration. Okay, any questions here so far?
No, all clear.
Okay, great. So next, I will write this CSV string, okay, into a text, txt. So this is not something I'm going to talk about really. Yeah, it's more about, you know, how to deal with this raw data processing. But when you write this to a txt, I can open this file. Okay, so it's called aligned txt. It will be here. Okay, so I just kind of write this, you know, CSV string into a txt file, separate thing, so that I can deal with the data here. So different types of events. You know, you can see control here. The program means the instrument. Okay, this encodes the instrument, the time signature, key signature, and tempo, etc. Okay. So df is the data frame. So now I'm reading this text file as the data frame. Okay. So what I did is I write this CSV string into a txt, and then I encode the txt into the data frame. So PD is the pandas data frame. So you read this file, my text file, and then you give different name, okay, of different tracks, different columns. And this is my data frame. Okay, so far I have a table, or I have a data frame, you know, for this MIDI file, and then I can really do different operation in this data frame. Okay, for example, I can group by type. So type give me different, you know, events. So we can see how many events are here. Okay, we have control, we have end of file and track, header, note on, poly after touch, program C, etc., etc. Okay, so what do they mean? Okay, what's these types mean, and what do they encode? So in order to understand that, there is a file. You will basically use this MIDI-CSV is their documentation. If you scroll down until this part, okay, it's called MIDI-CSV file format. Then you can read the documentation by yourself. Okay, then you understand what different types mean and what different kind of encoding mean. So for example, we have different names, right? So this the third field is the event name. So if you have header, you have different formats, number of track division, and these title T, they are all texts. Maybe, yeah, you can see here, time signature, and yeah, these are the kind of values telling you what the time signature this file is, and key signature, and tempo, okay, and note on, note off, pitch bend, and we also see poly after touch, right, in our control. And maybe if you wonder what is poly after touch, then you can find this thing in this file. Okay, here is poly after touch, the channel note value, kind of, it tells me, yeah, those capable of playing multiple notes simultaneously, often provide independent aftertouch for each note, yeah, etc., etc. So if you really want to do this task by yourself, then the best way is just, you know, doing this group by type. And if you don't know any type of them, you just look up and learn by yourself, and then you understand, okay, what the number mean, what these kind of different things mean, and how I deal with this. So in my work, I will only pick some of those events, okay, some events that's useful for my data processing. But for you, if you don't know anything, just look it up, okay? This is the best way to do. So I will pick several typical events, and we will look into them together, because they will be useful for in the scope of my work. Okay. So first is header. So the header will be kind of the first information you see, right? The first thing is header. So there will be 3 fields, yeah, different numbers. What they mean? Okay. So in the header, you will have 3 fields. They are called format, number of tracks, and division. Okay. So the first record of a CSV MIDI file is always the header. Parameters are format. So what is format? Is the MIDI file type 0, 1, or 2. Number of tracks, the number of tracks in the file, and division, the number of clock pulses per quarter note. And the track and time fields are always 0, okay? Which means the first 2 fields are always 0. So how do we get this header from our data frame? We will use this comment. So we see, okay, we want this type called header, and I will extract all the header from my data frame, and you can see I get 1 output, right? And here I gave different names, but the name doesn't really matter. We have kind of 3 fields here, 0, 1, 480. So in this work, the important thing is division. Okay. So so the most important information is the division, which we call it pulse per quarter note. Okay. We call it PPQ, which pulse per quarter notes. And this is the this thing, okay? This is the computer time, or the MIDI time we refer to, okay? Here. So we see, okay, we want header velocity is the last, is this field, and we get this PPQ, or the division is 480. So what does it really mean, the computer time, and what does MIDI time mean? So it means for every quarter note in this file, for 1 quarter note, we will use 480 samples, okay, to sample it. So this is our unit. I don't know if this is clear, but if you know sampling rate, right? The standard sampling rate of computer is 44100 hertz. Okay, so it's like you sample 44,100 hertz. Okay, and you sample this many numbers per second. Here is similar idea as sampling. So you sample 480 numbers per quarter note, every quarter note. Okay, so this is the MIDI clock pulses. Okay, per quarter note. And this will be helpful when we talk about time, okay, later on. So the next thing is tempo. Okay, so again, this is the track and time and tempo, and there's only 1 number. Okay, so this number is specified as a number of microseconds per quarter note. Okay, so here it uses microseconds. It's actually a very precise time. Yeah, if you think about our perception is most like in milliseconds, okay, the level of milliseconds. But here, the computer uses microseconds to encode time, and the number is between this value and a value of 5 100,000 corresponds to 100 quarter notes or beats per minute. So actually the tempo here give you BPM, right? You can compute BPM from tempo. How, right, is this to convert beats per minute to a tempo value, take quotient from dividing 60, how to read this, 60 million by the beats per minute. Okay, I'm sorry, I'm not good at the reading numbers, you know, in English, but this is basically what it means. So okay, I will demonstrate this here. This is how you compute this BPM. So whatever, let me get tempo first. Okay. Okay, again, I'm extracting tempo from my data frame, and this is the tempo of my file. Okay, wait. Seems I didn't get this thing in. Okay, here you go. So in my file, there will be multiple tempos. Okay, why? You can see these different tempos correspond to different time, right? The time stamps. Because, you know, during this, you know, during the music, during the performance, even the tempo can change, right? At certain time points across the corpus, which means the BPM can change. It doesn't have to be 1 BPM for the entire corpus. It can change, you know, in the middle. So in this example, it changes at this time, okay? But we only take the first one, for example. So I'm going to take the first tempo value here. So my comment will be tempo value, and 0 is a position. Okay, 0 position means the first one. And I call it MSQ, means microseconds per quarter note. Okay. So we have this number here. And how we compute BPM as illustrated here, right? We take the quotient dividing 60 million. Okay. And we use this number to divide our MSQ. Because MSQ means microseconds per quarter note, right? So how many microseconds are there in 1 minute? Is this number, right? There's this many microseconds per minute. So this is milliseconds, seconds, and you have 60 seconds per minute. Okay. So you have this many microseconds per minute, and which if you divide MSQ by this number, then you get beats per minute. Okay. Every minute, how many beats are there? There are 80 beats per minute in this corpus. And this is corresponds to this BPM here. Okay, 80. Any questions? Everything clear? Yeah, I'm making sure I'm not going too fast and make sure you understand this properly. You can ask if you have any questions. And also, you know, for programming, you can also ask if you don't understand some of the comments here. Well, everything's cool. Okay, thanks. I guess, yeah, we have some programmer here, probably. Yeah. Okay, great.
Believe you. We believe you. Okay.
Okay, thanks. Yeah, because people have different backgrounds. I'm more like math kind of STEM background. So yeah, certain things are maybe easy for me. But yeah, if anything not clear, if you have any questions, just ask. Just yeah, doesn't matter. So we provide this workshop for people from all backgrounds. Yeah, there's no like kind of assumption of, you know, preliminary stage, and you have to know this, you have to know math or whatever. So what we will do is basically simple math, okay, not too complicated. Okay, so we talked about tempo, BPM, and the time here. Now we are able to talk about the time in this file. Okay, go back to my slides. here. So we talk about MIDI, like PPQ, right? Pulse per quarter, and MSQ is microseconds per quarter. And then it means we have a kind of link, right? The transformation of units between these three different times. And then we can encode the time in this MIDI file using these different kind of, types of time. What we'll do is next, we'll deal with the notes. Okay, this is the most important event in a MIDI because we are dealing with symbolic music. Most important thing is note, right? Note on, note off. And the pitch, the note value, and velocity and time. Okay, so what does it mean here? So we have three different fields, right? Channel means which channel of music you are at, and note is the pitch, the MIDI number, velocity is the dynamics, okay? So here, again, I'm going to extract the note on event from my file. And if you look into the file, you will notice there is only note on, there's no note off, right? So you will wonder, like, if I have a note on, how can I don't have a note off? Then the note will last forever. But actually, no, because there will be two different types of encoding of MIDI. One is use both note on and note off, and then okay, so for example, my first note is 43. I know when it's on, okay, it's on time 0, and it will be off at 120, something like that, okay? But there is also another kind of encoding where you only use note on. You don't have note off, and then you denote the note off when the velocity becomes 0. So here, when the note is on, the velocity is 100. When the note is off, the velocity is 0. So when the dynamic is 0 means there's no sound. When means your note is off here. Okay. Then you can find this pattern here. Okay, I have a note 50, and it's on at 120. So the time is in the pulses. Okay, it is the MIDI time, the pulses, and then it's off 240, etc., etc. Okay, so all the notes follow this format. So in this processing, what we will do is that I will write out the note on and note off to different data frames. Okay, so that I can deal with them separately. So this block here actually do this one thing. So I get this file and I just say, okay, now I want note off, and I want when the velocity, note on velocity is 0, then when the velocity is 0, then I write the note to my note off. Okay, so I give another data frame called note off. So let me run this. So if I do that, you can see previously in my note on there will be 1, 3, 1, 2 rows, and now because I write note on and note off separately, then naturally this will be halved, right? Then I have 656 rows for note on and 656 rows for note off. Okay, and the length are always the same because when you have a note on, you definitely have a note off, right? Your note won't last forever. So this is a rule. So if you want to check if you program correctly, this will be a kind of a baseline or landmark that you can check. Okay, if I get this note on equals the length of note on equals the length of note off, I know, okay, I'm on the right track. If they don't equal, if this print false, then you know you made some mistake in your programming. Okay, so for the channel, we don't really use the channel in our work here, in this work, because the corpus I use is this one. Okay, so the channel means that there will be 3 channels. This is first, second, and third. Okay, the channel basically means different tracks. And not really different tracks, but different. If you have one track, so in this thing you have one track, only one track, but you have 3 different channels. And for kind of we listen to music on computer or whatever, you have 2 channels, left and right, right? So it goes into a left ear, right ear. things like that. So it depends on, there is no kind of definite way how you will encode this. It basically depends on people who encode this thing. So I assume in this thing, let me check, okay. Okay, so here, if we go to header, actually, I think you have number of tracks. Channel is 1. No, not channel is 1. Format number of tracks. There's 17 number of tracks. So yeah, it's kind of messy. It's not like you can definitely say how many channel will be there, how many tracks will be there. But here, yes, you can see there are 0, 1, and 2. So okay, so 3 different channels, which corresponds in our score 3 different lines. Okay. Yes. So thanks for the explanation of channel. Okay, great. Okay, thanks. So let's continue. Thanks for the question. Okay, but here, so we have 656 nodes, basically, right? Nodes on, nodes off. So we have this many nodes in this score. And now we can compute time. So let's see, for the first position on node on, which is this node 43, and we have this time on at 0 and time off at 120. Okay, so we see this clock, the computer time, the clock pauses. Then we see, okay, on-site, I want to know when is the on-site, and I say, okay, node on, I'm calling time, and this is 0. 0 means the first position. Okay. And I want to know the offset. I see node off, time, and a 0, which means, you know, the first position here. Okay, the time is 120. And then I just subtract the 2, right? The duration will be offset minus onsite. Okay, very easy. So I get 120. Now 120 is clock time, is the clock pauses. How do I transform this duration into quarter length and also the real time, right? In the seconds or milliseconds. So what we'll do is I will divide duration by PPQ, pulse per quarter. Okay, and then if we divide this number, what we will get is the length, the duration of this node in quarter length. So here I get 0.25, which is 1 quarter. So this means 1 quarter of a quarter node, which is 16th, right? 1 quarter of the beat. Okay, so 120 equals to 1 quarter. 1/4 quarter node is the 16th node, and this corresponds to our file here, right? Our first node is the 16th node. It's 1 quarter of 1 quarter. Okay, so it's 16th. And how do we compute the real time? I mean, real time means, you know, the time we use, like in seconds, is that we will multiply this duration by MSQ, which is microseconds per quarter. So if we do this and we get this number, it means like we have 187,500 microseconds for this node, which means 0.1875 seconds, right, in real time. Is this clear? Yeah. So this is how we transform different units of time in MIDI file, okay, as outlined here. So we have 3 different units, and this is how we transform between them. And after knowing this, after we know how to compute this, we can incorporate this into our data frame. So what we did here, you can see in my new data frame, I'm using different time notations. So this time on is the previous one, is the computer clock pauses. Time on quarter is the time computed in quarter length. this IMS in this is called it's actually microseconds. It's not milliseconds, okay? Yeah. If this is somehow confusing, I'm sorry, because yeah, I use IMS because microseconds actually use US, but fine. And we keep channel, nodes, and duration. We add something called duration here. So duration, we have 3 types of duration, right? Clock, computer time, quarter length, and microseconds. And also, we will use the computation here. You can see for the time on quarter, we use time on divide VQ. For microseconds, we just multiply MSQ as what we did here, right? The formula here. And let me run this thing, then run this thing. Okay. Now in this data frame, we can see for durations, right? We have different durations. Yeah, because in our example, most nodes are 16th nodes. So they are of 1 quarter, and this is the, you know, the microseconds, they last. So what's the next step after getting the duration? So after we know the duration, and we kind of know that this corpus is actually 1 line, okay? So it's monophonic, and this is kind of, you know, one note concatenated to the next one. So this is actually called stream, music stream, which is just, you know, one single monophonic line, and the notes are concatenated one after another. Okay, so there might be some rest, but in our case, there's no rest. Okay, it's just one note after one note, and they just concatenate together. So in Python or in Jupyter Notebook, we can use something called stream. Okay, so this is from the package music21. Okay, from package music21, we have a function called stream, and in this function, okay, we can set up the tempo. So I set up the tempo as my BPM is 80. Okay, and then use append. Append means, you know, one note after another, and I concatenate them in time. Okay, then it forms a stream, and my instrument is shallow. And then I can specify the note, the pitch, the duration, and then just append those these notes. Okay, these 656 notes one by one, and then I can create this stream here. Take some time for the stream to show. Okay, so then you can see here, comparing to our original corpus, we have 3 channels, right? But here we only have 1 channel, 1 line, because it's encoded as a stream. Okay, and you can see BPM still 80 here. And I can also show this in MIDI. When I run this command, it will automatically open this MIDI file in my Muse score. Okay, because I set my default notation software is Muse score. But if you use other software, it will also open, yeah, in your own computer, yeah, in your own software. So this is what I get, and let's listen to this. Okay, so this is the same, yeah, the same composition as before. It's only like we just use one single channel, one stream to denote this. Okay, so what's the merit of writing this? Of course, there are a lot of things you can do, right? I mean, you can change the instrument. Here, I mean, if I change the instrument, then I can play this using different instruments. If I change tempo, I can use different tempo. So I can manipulate this using my programming. Okay. But But you can also do the same thing here in some software. Yeah, if you find the comment, like instruments, okay, maybe I can change my instrument here. Also, for BPM, I can also change this here. But I mean, if you are a programmer, if you want to do this, you know, in this original format, so this is what you can do. It is one way you can do it. So we will come back to this later on when we talk about BPM. But for now, let's just leave it here. Okay. Okay. I hope everything is clear so far in terms of pitch and duration, especially duration. Okay, especially time. It is very important. Okay, how you know how to compute time, how to process this data. Okay, so now let's continue. Okay, great. Thanks for the feedback. So yes, so someone mentioned, right, the metrical structure, the bit level. Thanks for that, because not many people will really think about this. Actually, for many kind of, you know, people who do this symbolic music generation, they don't really consider this because, well, maybe they don't have enough this musical background, or they just don't care about this thing because because this is not in the MIDI file, right? If you read the MIDI file for the note events, the only thing you have is time. Maybe I should go back here. Okay, yes, this thing. The only thing you have is the pitch note, the pitch, of course, the velocity, and the time. Okay, you don't really have this bit level or whatever in your MIDI file. That means if you want to use metrical structure, you need to encode this by yourself. Okay, and for many kind of data, data scientists, because for the music generation task, because this is very programming heavy, which means not many musicians will do this. And the programmer who started working on this task, they don't really have a well-trained music background, which means they're good at data frame, they're good at Python, and when they get this file, okay, they say, okay, I read the lines, okay, I understand what that means, and I just use what I have. Okay, so this is why, like, we kind of want to I kind of educate these programmers of more music background, music knowledge, and also provide musicians with the tools, because definitely musicians have better understanding of music, right? Like the people who just brought up this metrical structure, of course, you have this background that there is upbeat, downbeat, and there is metrical structure that I can utilize from the corpus. But for the programmers, if they don't have the musical background, they won't be able to understand this message. Okay, this message encoded in this corpus. But here, because we know this, there's something called bit level or bit structure or metrical structure. Okay, then we can use this information. Okay, so there are different kind of levels of the bit in this score, and I will use different colors to denote sorry, this is my okay, 1 minute. My clock. Okay. So here I use red to notate the meter level, which is a downbeat of every bar, every meter. Okay, this is in red here. And I use green to denote the beat level. So every quarter note or every beat. So every downbeat of the quarter note, I use the green color. And for the 8th level, okay, the next level, I use blue. So the blue is actually the upbeat. If you consider I mean, normally people call this downbeat, right? The downbeat of every quarter note, and this blue thing is the upbeat, considering the 2nd level. But if we go to the 3rd level, we consider this as the 8th note level. The blue note will become the downbeat, on this 8th note level, and then the green one will become the upbeat. I hope it is clear, right? So if you think about this as the 8th level, then your blue note will become the downbeat, and the green one will become the upbeat. And if we go to the 16th level, the green one will be the downbeat, and the 32nd will be the upbeat. So downbeat, upbeat are relative, considering the scale you are talking about, right? The beat level. So there is a hierarchical beat level here that I can just kind of denote like this. And we can, if we can process this information, if we can utilize this, and then we can input this as some additional information into the neural network or just the generative system, then probably I can generate better corpus, right? Because now the computer has more information from me or from the data set, and then it can understand more of the music, and then it can help the computer to generate better better music. So how do we do this? How do we get this? So this is how. So this kind of bit level are largely dependent on the time signature. Okay, so you have the time signature here as 4/4. Then you know, okay, I have 4 bits per measure, and every bit is a quarter note. And then I can compute, at least I can compute the meter level, right? It's every 4 bits, I have a right note. And for every bit, there is a green one. And after that, I just divide 2, right? I just divide 2 to get 8th, divide 2, get 16th. So this is the idea of how we compute this. So first, we need to extract the information of time signature. Okay, here. So time signature in MIDI-CSV, so it has 4 fields: number, denominator, click, and notes Q. What we will use mostly is the number and the denominator, or the number, numerator and denominator. Okay, so because time signature is represented in this format, 4/4, like 3/8. You always have a numerator and a denominator. For this click and notes Q, I mean, they have their own meanings, of course. But here, yeah, I'm not going to give more introduction to this. Sometimes it matters, but in the scope of this work, it doesn't really matter. And so we will focus on the most useful information, which will be, yes, so I'm extracting this information here. This is the 4 fields. So this is numerator, denominator, the click, and notes Q here. Okay. And then to compute the time signature, actually you can see the denominator is 2, right? It's not 4. Why? Because the denominator is actually represented as the power of 2. Okay. So here you can see numerator gives the numerator of the time signature as specified on sheet music. Denominator specifies the denominator as a negative power of 2. For example, 2 for a quarter note, 3 for an 8th note, etc. Which means the number here is always used as the power of 2, which is given here. Okay, so when we compute the time signature, we'll use the numerator directly and divide, and then the denominator will be 2 of the power of the number here. So if you have 2, 2 of power 2 is 4. If you have 3 here, 2 of power 3 is 8. Okay, then you can print this time signature is 4/4. So after knowing this, I can compute the bit number per measure is 4. Okay, I have 4 bits in every measure, and every bit is a quarter note. Okay, the bit quarter length is 1. And if we multiply them together, we get measure quarter length. So every measure is 4 quarter notes. Is everything clear here? Okay. Yeah, if you need more time, or if you If there's anything unclear, just let me know. Okay. So it's basically how you compute the time signature in MIDI. Okay. Okay, thanks for the feedback. I'm just wondering if I'm really seeing this clearly. Okay. So 4 beats per measure. Every beat is one quarter note. Okay. And then this will be the formula, the program, how you compute the beat level. Okay. So you have onset, you will divide the measure quarter length, and this gives you level 0. Okay, this is the first level. So this level gives you the right note here. Okay, the right note here. This is the note of the metric level. And this is the second level, is the beat level. Okay, that's why you divide beat quarter length, and then you get this level. It is for the green color. Okay, downbeat of every beat, and then after that just divide 2. Okay, but divide 2 and get the 8th note level, and divide 2 gets 16th, divide 2 gets 30 seconds, etc., etc. And then I will write it to another data frame called beat level. Okay, so here you can see I use different colors, how I pick up the color, and again I use the stream. Okay, so everything here is the same as before. I just use different color to denotate the notes. If I run this, okay, I get this thing in my slides. Okay, so now we have actually 3 types of information, right? One is note, the pitch, the note value. One is the duration, right? The duration for each note. The third one is the metrical structure. So actually here we use the metrical structure or the bit level to kind of replace the velocity. Okay, because we know in this file the velocity is the same for every node, and we don't want it. We want some kind of dynamic. And how to do that is that we can basically say, okay, I probably give this downbeat more kind of velocity, like accent, right? More velocity, and give the upbeat like lighter velocity. So it works sometimes. It sometimes works. So we can probably design different velocity for these different nodes, and we see, okay, maybe for the red one, the velocity is 1, the green is like 0.8, is 0.6, 0.4, things like that. It works in certain circumstances. I mean, this is one alternative way of doing this data processing, right? Another way, I mean, more importantly, is that this extra information can be encoded into your generative system. Then I'm saying that except for pitch and duration, I'm providing or inputting another additional information that can help my computer to better understand my my corpus, right? How the music is composed, and this will assist the computer to. I mean, more information is just, better, right? There's no loss of information. The computer gets more information, the better it may understand the structure of the music. Okay, so I think this is the first part of this music data processing. Our next part will be on music generation. So I will briefly talk about the system neural networks, but we won't do this in much detail today. So in tomorrow's workshop, I will talk more in detail of the neural network. But today we'll just look briefly look into the structure and just let you have an intuition of what is a recurrent neural network. So I think maybe we can take a break of like 15 minutes. Yeah, I think okay, so let's come back at 9. Okay, it's 9:35 for me, But let's come back after 15 minutes from now on. Okay, 15 minutes. Okay. See you later. Thanks. Okay. Okay, great.